Swayam Prabha. Digital India. Educated India.
Okay. So, if epsilon times 2 psi to the power 2 k is less than or equal to psi minus phi, then a k of psi minus epsilon is less than or equal to psi minus epsilon times 2 psi whole to the power 2 k. Okay. So, epsilon is some parameter. So, we are trying to parameterize this difference over here in terms of k. So, as for different values of k, we want to show this. So, the proof is by as you can guess, it is by induction. So, this should happen for all k. So, we will prove this by induction on k. Okay. So, at k equal to 1, what happens? So, at k equal to 1, observe that we do not even need the hypothesis over here, the left hand side and the right hand side are equal. So, a 1 of psi minus epsilon is psi minus epsilon, like as I said. No, I think I need 0. So, a 1 will be difficult. Yeah. So, let us take the base case as 0. Yeah. So, a 0 of psi minus epsilon is equal to psi minus epsilon, and if I take k equal to 0 over here, I get psi minus epsilon as well. Okay. Now, assume that it is true for all k minus 1. So, now let us look at k. So, a k of psi minus epsilon. So, first I will use the inductive definition of a k. So, a k of psi minus epsilon is nothing but a 1 a k minus 1 of psi minus epsilon. Now, by induction we know that this is at most a 1 of psi minus epsilon times 2 psi to the power 2 k minus 2, right. I am just substituting the value of a k minus. So, here I use the definition of a k, and here I am using the inductive hypothesis to substitute for a k minus 1, okay, this value. Now, what do we do? So, we have this and we want to write down. So, basically we want to get rid of this a 1 over here, okay, and it should kind of give a another 2 side square term over here somehow, okay. So, what we will use is the mean value theorem over here, okay. So, recall what the mean value theorem says. So, okay, let me write down what the mean value theorem is. Okay, let me just use this portion, I do not need. So, do you recall what the mean value theorem is? So, suppose if I have a function f, a function which is continuous and differentiable in some interval a to b, then what it says is that there exists a C in the interval a to b such that f prime C is equal to f b minus f a by b minus a. Okay. So, if I have a function which is differentiable in the interval a to b, then this holds. Okay. So, what do we get from here? So, from here we will get, so now what do we consider as b and a over here, right. So, what we want is we want a 1 of psi. So, this is something that is good for us because a 1 of psi is nothing but psi, and we will get epsilon times 2 psi 2 k minus 2 times some a 1 prime of some theta for theta in this interval by mean value theorem. Okay. So, let us quickly check this. Okay. Let us just verify this. So, okay, we just use this place over here. So, I have these two terms, right. I have a 1 of this and I have this. So, basically I will choose this quantity to be my b over there, and this quantity, no, this is actually smaller, right, for psi minus. So, this quantity is my a and this quantity is my b, right. So, this minus this, okay. So, f b minus f a is nothing but f prime c times b minus a. Okay. So, and what is b minus a over here? So, b is psi. So, psi minus of this quantity is nothing but epsilon times 2 psi to the power 2 k minus 2. Okay. So, this is the consequence of mean value theorem, and this is equal to, so psi is a fixed point. So, I get psi minus epsilon times 2 psi to the power 2 k minus 2 times a 1 prime of theta. And now, what can we say about a 1 prime of theta in terms of, let us say, a 1 prime of psi? So, look at the graph for a 1 prime. Okay. So, this is the graph for a 1 prime. So, this is where a 1 prime of psi lies. Okay. So, this is the value of a 1 prime of psi, and we know that a 1 prime of psi is 2 psi whole square. What will a 1 prime of theta be? More than a 1 prime of psi or less than a 1 prime of psi? Where does theta belong to? Why? So, theta belongs in this interval between phi and psi. Okay. So, in this interval the value of the function is more than this quantity. Okay. So, if this is now we can use the same upper bound. So, I have a negative over here. So, this is upper bounded by psi minus epsilon 2 psi times 2 k minus 2, and I will just skip a step over here. So, a 1 prime of psi is lower bounded by a 1 prime, sorry, a 1 prime of theta is lower bounded by a 1 prime of psi. A 1 prime of psi is 2 psi whole square. So, this I can write as times 2 psi whole square, which is what we want. Exactly. Okay. So, this proves the claim. Okay. So, essentially what this claim is saying. Okay. So, let us try to see what the what we get from this claim. So, for that we will just substitute some values. So, let epsilon be. So, what is epsilon over here? I am using psi minus epsilon and I want to get this quantity, right. So, I will choose epsilon to be 1 minus psi over n, and I want the term, yeah, on the right hand side in some sense I want it should be bounded by this log n thing. So, for the right hand side I will choose k to be equal to log of phi psi minus phi. Is this correct? Phi minus psi divided by epsilon to the base 2 psi. Okay. And k is a variable for us. We haven't said like what how many levels we need. So, I will just set k such that 2 k is equal to for us it should be equal to 3.28 times log n. Okay. So, essentially k is 1.64 log n over here. So, yeah, so essentially note that, so epsilon was a variable for us, right. So, we can choose, so and epsilon and k both were variables for us. Okay. So, we can choose what value of epsilon and what value of k we want. And why do we want this value? So, now let us just substitute these two values in the claim. So, what we get by substitution is that a k of phi minus epsilon. So, sorry, psi minus epsilon is psi minus 1 over psi by n is at most psi minus epsilon times 2 psi to the power 2 k. So, 2 k is this quantity. So, 2 psi to the power this quantity would be nothing but, so we have epsilon times psi minus phi by epsilon. So, these two cancels out. So, this is equal to just phi over here. Okay. So, this is the reason why we had this complicated choice for 2 k, because we want this to boil down to. So, this should be at most phi. Okay. And what is phi? So, we know that the value of phi is 1 over root 3, right. So, it is like 0.58. Okay. Now, observe that what happens if I apply a k again to this equation. Okay. So, I have a k of this is equal to this. So, essentially what I have by the claim is that in these many levels, okay, the value of the output value of a k for this argument would be at most phi. Okay. Now, actually I want this to come down a little more. Okay. I want this to be less than 1/4. Okay. Now, observe that if I apply the function a, the amplifying function a again on both left and right sides, it kind of decreases the value. Okay. So, by applying A1 a constant number of times to the above equation, we get the right hand side to be less than, or well, I can keep it strictly less than 1/4. Okay, we need it to be less than 1/4. So, we will just apply, because I mean again you can check this. Okay, so if you apply A1 on 0.58, you will see that it is decreasing, and just by applying some, I think few number of times, this will becomes this will be less than 1/4. Okay. Now, why do we need that to be less than 1/4? So, this is where we use a second claim. I have already written 2, so 3, claim 3. AKP is less than half of 2p raised to the power 2 raised to the power k for all k greater than or equal to 1. Okay. So, this proof is also quite simple, just by substitution. So, for k equal to 1, you can see this easily. So, A1p is nothing but, what was A1p? A1p was 2p square minus minus p to the power 4, right. So, essentially it is less than or equal to 2p square. So, on the right hand side I get half of 2p square. Okay. So, for k equal to 1 it is clear. Now, let us look at for k equal to 1 is done. Now, let us look at any arbitrary value. So, AKP definition is A1 of AK minus 1p. So, if I apply induction, I get A1 of, this is strictly less than half 2p raised to the power 2 raised to the power k minus 1. Now, I apply the definition of A1, I get 2 of half 2p raised to the power 2 raised to the power k minus 1 over here, and I will just, so the other term is anyway just makes it smaller. So, I will just use less than or equal to and leave out the p to the power 4 term over here. And now, if you just simplify this, you will get that this is equal to half 2 p whole to the power 2 whole to the power k. Okay. So, the point is, it is just a straightforward simplification of this definition of A1. Okay. But what does this give us? So, what this gives us is, that is what is more important. So, we are almost there at the proof. So, what this gives us is that if I take p as if I take p to be less than, or if I take p to be, let us say 1/4, for example, or even less than 1/4 would be fine, but it is okay. If I take p as 1/4, what I get is a k of 1/4 is at most half, 2 times 1/4 is half to the power 2 to the power k. So, this is at most 2 to the power minus k. Okay. So, okay. Now, what was k for us? Okay. So, now we can choose k to be anything. Okay. So, now observe what is happening. So, I have this formula, big formula. So, first in some two k equal to 3.28 log n many layers, I get a probability that is less than 5, right. Next, I said that some constant many layers, I get it to be less than 1/4. Okay. And now, I am showing that if I start at 1/4, now if I choose k to be another log n. Okay. So, if I take k equal to another log n many layers, okay, I will get the probability that this whatever this outputs a1 as being less than 2 to the power minus n, if I take k to be log n. Okay. So, how many what is the number of layers? So, here I have a 1 point, here I have k equal to 1.64 plus some constant, and here I have another 1, okay, times log n. So, this is equal to 2.64 times log n. So, this is the value of k, and 2.64 times log n means that the total depth is this times 2, because for every value of k I have 2. So, the total depth is equal to whatever 5.28 many layers. Okay. So, what we have shown is that in if 2k is greater than or equal to, well, I have 5.28. So, I had just 5.3. So, if it is greater than or equal to 5.3 log n, then a k of phi minus 1 over phi by n is at most 2 to the power minus n. And as I said, the other direction is just symmetric. You can go through the proof and figure out where you have to make changes in order to make that work. That would be a good exercise to understand the proof as well. Okay. Now, once this lemma is proved, how do we get the main theorem? Okay. So, now observe that okay, I will just take couple of minutes because I want to complete this. So, once we have the lemma, the main theorem is actually pretty obvious. It is just by a probabilistic argument. Okay. So, fix an x, okay, some x. Now, suppose that majority of, assume that majority of x is equal to 1. What does that mean? That means that the number of ones in x is how many? How many ones do I have? It is greater than half, right. So, we can say that it is, and assume that well, x is odd, the length of x is odd. So, it is greater than or equal to n plus 1 by 2, okay, the number of ones. Now, what is the probability? So, what else do we need? Okay. So, what is the probability that for a randomly, I mean for this randomly chosen formula, a leaf gets value 1, right. Okay. So, what is the probability that a leaf gets a value 1? So, we have this randomly chosen formula that we saw at the beginning. Now, how do we assign, how does a leaf get a value 1? So, it gets a value 1 either if we assign it a constant 1. Okay. So, that happens with how much probability? 2 psi minus 1, or it will get a value 1 if one of the variables is 1 in this fixed x. Okay. So, for this x. So, what is the probability that a leaf that a variable gets a value 1? So, there are twice 1 minus psi many variables, and at least these many of them are 1s. Okay. So, it is 2 and the total number of leaves is n of them. Okay. So, this is the probability that a leaf gets a value 1, and if you simplify this, this turns out to be psi minus 1 minus psi over n. Okay. You can check that this evaluates to this. So, this is the probability that a leaf gets a value 1. So, now the probability that, so if this is the value of a leaf, the probability that okay, fine, the formula outputs a 1 is greater than a k of psi minus 1 minus psi over n, which is greater than. So, this is greater than this quantity, right. So, this will be plus over here because it is outputting. No, 1 second, let me just verify. So, this will be actually psi plus 1 minus psi over n. So, I have psi plus 1 minus psi over n, and this is 1 minus 2 to the power minus n. So, the probability that the formula, so this is for x. So, the probability that the formula outputs 0 on x is at most 2 to the power minus n. Now, I just take the union bound. So, the probability that formula outputs 0 on some x is at most, there are 2 to the power n many different x's times 2 to the power minus n, which is at most 1. Okay. So, and the negation of this is nothing but what we want, that the probability that the formula outputs a 1 on all x is greater than 0. Okay. And this implies that there exists a formula for majority. Okay. So, this argument is again exactly the same as what we gave for Andreev's function. This is the standard argument by applying the union bound and showing that well, the probability that there exists a formula that works for all x is greater than 0, which means that there is some formula which is there, okay, as I said. So, this completes the proof of the entire theorem. Okay. Yeah, sorry, I actually overshot the time, but I wanted to complete this proof. So, again, so just going back a little bit. So, the main idea is this amplification, right. So, the way this formula is constructed is very clear. Okay. So, it is a very easy to construct structure. I mean, the structure is very easily defined, but the argument is how do I argue the value that the formula takes at various levels. Okay. So, the way we argue to be able to argue, we use this amplification function, and we show that at each level the value kind of the probability kind of gets amplified. Okay. The probability that it outputs the correct value. So, finally, I get the correct value is something that is positive. Okay. Okay. So, that is all. So, any questions? Yeah. So, just a couple of points. So, there are a few things which the argument was symmetric, of course. For example, I did not prove it for this other case, but as I said, please make sure that you verify it yourself. You go over the proof by yourself. It is not very difficult once you have understood the idea, and make sure that for the other cases as well. For example, here I showed that if a k of it is 1/4, then it is less than or equal to 2 to the power k. Then you can also show that if you take p as 3/4, a k of 3/4 will be greater than or equal to 1 minus 2 to the power minus k, okay, because you need that argument for the other direction. Okay. So, 2 to the power 2 to the power k, right. So, k is log n, right. So, minus okay. So, the minus is fine, 2 to the power k, correct. Okay. So, I will stop here.